Yes, Rohini, please go ahead.
Yeah, so first of all, very, very fascinating discussion. A lot of interesting thoughts, comments. I guess my question is maybe more general, that some of the discussions you had earlier in the conversation on different paths to the state space that a system can take, and therefore the interaction, and you talked about entanglement, you talked about fundamental speed limits, especially in the context of computing. Are there ways to nudge the path the system takes in a state space? Are there some fundamental thinking that's happening there? Uh, and you talked about entanglement, talked about material, but how are people thinking about that in the context of also error correction? That's one of the sort of, I was wondering what the connection is between the two.
So
Uh,
you take this question, Adolfo, or?
It's a diverse one, yes. So I don't know which angle to take. So yeah. I mean, so this I guess speed limits are being used in very diverse ways. I don't remember now. Any physical operation, including the error correction, is going to be restricted by these speed limits. I know in I mean, so there was like error correction, there was materials and entanglement. Entanglement, I think we already acknowledged that it's a resource, that it can speed the evolution, but it can be feeble, or it can be perhaps not robust to certain kinds of noise. Then if you are able to counteract this noise with error correction, then you may be able to restore this maximum speed. Now, the connection with materials maybe is harder, because there are very different angles. I don't think that from a point of view of material science, people are concerned with the speed limits at the moment. But what we know for sure is that if you are driving a system from one phase to a different phase, like a bunch of spins from a paramagnet to a ferromagnet, you may be crossing a phase transition, and then you can again formalize these ideas of information geometry, try to identify proximity between these phases, and study speed limits. And as we know already from classical thermodynamics, things like the heat capacity diverges at a phase transition. And so this also reflects on the quantum Fisher information, or in the quantum speed limits, in the quantum speed actually. So there's also a divergence. And this is very important for applications in computing, because this simple example of going from a paramagnet to a ferromagnet is kind of a completely idealized process of a computation, where you try to prepare the ground state, which is the ferromagnet. The ferromagnet, yes. There is, in some sense, these ideas of crossing phase transitions and what are the speed limits for them are being used to inspire a family of quantum algorithms. So for instance, we know that using quantum control, we can saturate the speed limit. So we have done this for simple phase transitions. But then an elaboration of these ideas have given rise to a set of quantum optimization algorithms, which are called by now perhaps digitized counter-diabatic quantum algorithms, where you use some approximate controls to solve some optimization problem, which physically means we are trying to find the minimum energy configuration of a given complex system. And there again, speed limits and the possibility of saturate them is being used. I don't know to what extent that answers the question.
So maybe I can add from my own experience where speed limit can be of use, in quantum computing. So I'll give a very simple example, which I have found many years back. So if you think of this so-called Grover's algorithm, this finding this particular item in database. So we know it is optimal and it takes square root of n steps, right? So in that context, you can use quantum speed limit, and you can obtain exactly this square root of n step from speed limit. And not only that, you can also imagine your evolution of the quantum computer from initial state to target state as a sequence of evolution along the shortest path, you know. So what happens is what you can do is you can find the distance between initial state of the quantum computer in case of Grover search and the target state, okay. And then you find the distance between the initial state and the state at next iteration, okay. So since we know that it evolves along shortest path along geodesic, so if you divide the total distance by this distance in one iteration, I have shown that ratio exactly scales like square root of n. And so you can get the speed limit. Sorry, you can get the query complexity in case of quantum computing in this particular case from quantum speed limit. You know,
So then it should be possible for new algorithms also to estimate
yeah. So
this technique. Yeah.
right. So one of the major goal in quantum computing is to design your sequence of unitary operator so that you can drive your system along the shortest path. Okay.
Mhm.
So, yeah.
Right.